So, good morning, everybody. I wanted to especially thank the organizers for their invitation. So what I'm going to talk about today is a very interesting topic, I think, about recent observations by cosmic ray detectors that are significantly contributing into the atmospheric physics world. I thought it's interesting to note that we probably know C.R. Wilson by his cloud chamber invention and his winning of Nobel Prize in 1927. But what we probably don't know is that he did it out of his interest in atmospheric electricity to begin with, which fits in the theme of today. The experiment I will cover today are also in the Cosmic Indirect session with the times in here. The experiments I'm covering are LOFAR and the telescope array with a suite of lightning experiments that was added to it to study terrestrial gamma ray flashes. The significant observation by Graves 3 mu1 telescope in a gigavolt observation in a thunderstorm. And the very interesting, promising observations by OJ to study and understand and model ELFs better than what we have learned before. The main two topics I will cover today is lightning and high energy production in the atmosphere, like terrestrial gamma ray flashes and also transient luminous events. We are more familiar with lightning. In general, the main idea of how lightning starts is that you have charge separation. This is a phenomena that happens to us on a daily basis. We're walking on a carpet, charges separates, we touch a doorknob, and then you have an electric shock. This is the same thing that's happening right here, but of course on a much larger scale. One idea that could explain how these charges separate is you have light hail that is referred to as grapple. Passes through ice crystals. The ice crystals get carried away by upper wind into another upper layer. So you have charges separation of negative layer and an upper layer. And if that builds high enough, then you start having a conventional breakdown and you have lightning. This lightning is categorized in several categories that are important in the later on in the talk when I'm going to refer into these parts of lightning. Inside the cloud is referred to as intra-cloud lightning, and it happens 2/3 of the time. Charge induced in the ground producing cloud-to-ground discharge. That happens 1/3 of the time. And there is more rare type of lightning, which is not the propagation of the negative charge, but the propagation of the positive charge from the cloud to the ground. And this part is important for later in the LOFAR measurement. So usually when we talk about lightning, what we see with our eye is the main flash that happens. But before the main flash happens, there are several complicated developments of lightning before we see what we're about to see right now. And what happens is that you have lightning doesn't figure its way out to the ground directly. You have the electric charge building up, and then if you get an electric field high enough, electrons starts surging their way out of the, let's say, the negative layer into the ground in terms of steps. And this is why this part of lightning is referred to as the step leader. And it's the slowest part of lightning goes to take about 10 to 20 milliseconds. After this connection happens, when the lightning becomes close enough to the ground, it induces a positive leader that's going from the ground up, and a connection happens, and you have the return stroke. The return stroke goes for about 100 microseconds. And this process sometimes repeats itself several times. The whole lightning flash takes about a second, at maximum, that is. So the lightning initiation problem, what don't we know? We don't know how lightning gets initiated, and that's something that probably many people don't know. The heart of the problem of lightning initiation is electric field measurements. So it's either, what we understand is that break of lightning will happen when we have an electric field high enough of equivalent to the electric field conventional breakdown, which is about 3,000 kilovolt per meter. Measurements of balloons and aircrafts that have been going to study lightning haven't measured anything above 2 orders of magnitude less than that. So it's either something wrong in our understanding of how lightning starts, or there is something wrong with the way we're measuring the electric field. Now, if we focus a little bit on the electric field measurements, we have lots of challenges that we face because we're sending balloons and aircrafts into very violent environments. Thunderclouds are really large, and we're sending them into, of course, a small part of it. The electric field variation in time is in a matter of seconds. So the idea that we'll be at the right place at the right time of where lightning gets initiated is of low probability. But another important thing is that we are perturbing the system that we're observing by sending these balloons up in there. And so instead of waiting for the charge to build up like it should be, and we're sending the balloons or the aircraft in there, they're probably discharging them if we are at the right place at the right time to observe this phenomena. So with these challenges that that we're facing, ground electric field measurements, particularly from cosmic ray detectors, are contributing for the first time in a very unique way into modeling the electric field that hasn't been done before. LOFAR has a contribution into this field. They study cosmic rays by looking at the radio signal that is coming from them as they propagate in the atmosphere. There are 24 core stations. Every station has a 96 low band filter. These are the stations that are contributing into these studies that I'm going to show. And they are measuring the radio signal between 10 and 90 megahertz. So what LOFAR uses is the fact that when a cosmic ray passes through the atmosphere and you have the Earth magnetic field, then it bends the electrons and positrons, and you have an induced current that produces a radio signal above 10 megahertz in a coherent way that could be observed by these antennas on the ground. Every circle here is a station, and right here, this is the y-axis is V cross B, where V is the propagation direction of the cosmic ray, and B is the Earth magnetic direction, and this is V cross B. And what we expect is that the polarization is going to be in the V cross B direction. And most of the cosmic rays that they detect it to be polarized in the direction that we understand. However, they notice that for some of these cosmic rays that they observe, the direction is not in the V cross B direction, and that is correlated to thunderstorms that are passing on top of their detector. And that the parallel component of this electric field does not contribute much to the signal, but the part that contributes significantly to the signal, or mostly, is the perpendicular electric field component. Now, what they did is that they modeled the electric field on top of their detector, and it's a simple double-layer model where the electric field between 4 and 8 kilometers has a value that is about 50 kilovolt per meter, and is polarized in a different direction of the electric field that is modeled between 4 and 0 kilometers. 0 is the height of the detector. They integrated this model inside Corias and Corsica, and when they looked inside the events, they were able to produce the signal that is observed by the detectors on the ground very well. So right here, this is the cosmic ray power signal that is observed. So every big circle here is a station, and every small circle is an antenna, and the color inside the antenna is the power intensity. And the color scale behind is what is produced by simulation. So this is in fair weather, which is polarized in V cross B. And this is in thunderstorms. All the main features are reproduced well by the models that they made, the double electric field model that is polarized in different directions. So here, LOFAR is beginning to contribute in a very unique way in measuring, modeling the electric field on top of their detector without sending an experiment up inside the thunderstorm. Another very unique, which I thought was also a very interesting result by LOFAR, is related less to lightning initiation and more to lightning propagation. Lightning propagation inside the lightning world, they've been studying it for decades using two main methods: lightning mapping arrays and interferometers. The lightning mapping arrays map lightning in 3D, and there are 6 to 20 antennas separated by several kilometers apart. They are studying the signal, the impulsive signal between 60 and 66 megahertz. So if you're looking for processes like step leader and breakdown processes that are producing isolated pulses, this is your instrument. And every point right here is a source point that is reconstructed using the time of arrival method by the lightning mapping array. Now, another thing, the next method is the interferometer method. The interferometer method is a little different. It studies more of quasi-continuous emission. These emissions are more expected from the follow-up leaders, not the first step leader, but the leaders that happen afterwards, and it refers to as dart leaders. So these antennas are a few, 3 to 4 meters apart, and they're looking at the band between 20 and 80. And what they look for is they reconstruct the elevation versus azimuth. So you reconstruct the lightning in 2D, but with much higher time resolution. So this is what has been in the field before LOFAR. This is an example of a lightning flash that was observed by the two instruments at the same time. It has a duration of 600 milliseconds. LMA saw about 1,000 sources, and the interferometer saw about 60,000 sources. So this is the main difference summarized in this table. Anything below 3D, anything below 10 meters in 3D is a mystery. And this is where LOFAR now is coming into contributing significantly in the field in detecting lightning in 3D in a resolution, hopefully in the near future, comparable to what the interferometer is doing, but already higher than the LMA. And so this is an example of something exciting that they saw. So here you have a positive leader and a negative leader. Just a quick reminder, a negative leader is where the negative charge is making its way to the ground or up in the cloud, and the positive leader is the positive charge is making it. Now, positive leaders are studied a lot less, and we know a lot less about them. That's because they are less frequent, they are rare, and they're less luminous, so harder to photograph. And also, they produce less VHF. So in general, we know less about them. And LOFAR happened to see a positive leader and happened to be able to zoom in on it and gave us information that we didn't know about positive leaders before. So right here you see this is the positive leader. This is the gray line is where the positive leader is propagating, and it's not emitting radio signal. The way we're detecting positive leader is actually by seeing branches that are coming out of them. In terms of the negative leader, when you see a signal, you're seeing it coming out of the leader itself. So because of the resolution, they were able to zoom in on these branches, which is refers to as needles. And when they did, they found out information about the size of these branches, which help with modeling. But they also found out that they have a speed similar to the negative leader, which means that what they're seeing is negative breakdowns that are coming from the main positive leader. This information helps a lot with many models that are finally trying to explain how a positive leader propagates state on a much zoom-in level. But also, there's also another theory that says, okay, this probably can help us understand why lightning strikes twice in the same place, is that the main leader is not discharging completely. There is energy stored in these needles that is going in again and producing these double discharges that are happening in the same place twice or several times. Okay, so the main message is LOFAR is probing the electric fields in ways that haven't been seen before. And also, it has an unprecedented precision in looking at lightning propagation, in which it helps us discover new things about a phenomena that was little understood before. Another important topic, which I think the cosmic ray detectors are contributing quite significantly to at the time, is terrestrial gamma ray flashes. Now, we all know lightning, but what we didn't know before Abbasi in 1994 is that we are seeing gamma rays that are coming out of our own atmosphere. That was a very exciting result back then, and it was followed by several satellite experiments that had dedicated filters to study terrestrial gamma ray flashes like RHC, Agile, and Fermi. And they have been seeing thousands of TGFs by now. And what they have reported to us is the following, that what we see of lightning is more correlated to the leader stage. What we see of terrestrial gamma ray flashes is correlated to thunderstorms, and more particularly to leader stage of lightning. Also, that they have a duration on average of 100 microseconds, and on extreme from 10 microseconds to 1 millisecond. Another thing is that in addition to their energy being higher than 100 keV, from simulations that have a few assumptions on the height and the opening angle of the source, that's the source of the electrons that are accelerated and producing gamma ray via Premis-Strahlung. There is about 10 to the power 14 to 10 to the power 19 particles. You can see the range is quite high. That's because the variations in the assumptions in the simulations are also quite high. Many theories try to explain what we see of high energy. So we can start with Wilson runaway electrons. So here you need seed electrons, assuming that there is a cosmic ray passes through a thunderstorm with high electric field, produces extensive air shower particles. So you have these free electrons now. And on the y-axis is the frictional force, or the energy loss per unit length. And on the x-axis is the energy of the electron. And the solid line here is energy losses via ionization. And the dashed line is the energy losses via Premis-Strahlung. Now, if you have your particles going through a thunderstorm with an electric field equals to what's referred to as the break-even electric field, then your particles will get accelerated to an energy equal to the minimum ionizing energy. This is why it's referred to as the break-even energy. What we know is that in order for us to have lightning, then we need an electric field about the conventional breakdown, which is about 10 order of magnitudes more. And what you will have is all your particles with energy higher than E threshold will get accelerated to energies that could possibly produce lightning or X-rays. If it's in this area, then the energy losses dominate and you won't have acceleration. You can see that if your electric field now is higher, the E threshold goes lower, and you have more particles that get accelerated inside your system. And if you have your electric field higher, when it's referred to as the critical electric field, then all of your free electrons are going to get accelerated. This is what's referred to as the thermal runaway electrons. And the theory was like a combination of thermal runaway electrons as seed particles in addition to runaway electrons will produce the X-ray observations that we see. But because the Wilson-Renaway electron accelerates one-to-one particle, we need an avalanches of particles, and this was suggested by Gouffrich in '92, in which he said, okay, so we didn't include molar scattering inside this information, and if you have molar scattering and the electrons are get to an energy higher than the E threshold, then you start to have an avalanches, and these avalanches are number about 10 to the power 5 to 1 particle at the source. So this, by itself, this process is what's referred to as relativistic Renaway avalanche. Needs seed particles at the source, which could be cosmic rays or could be thermal runaways. Another suggestion by Dwyer is that, okay, so in addition, we didn't take into account positive feedback from photons and positrons that are produced in these processes. And if you take these productions into account, then you can produce TGFs at the energies that we see by satellites. For this, you need a high voltage, a higher voltage restriction than you need for the rest of the topic. So here is a summary of all these processes, and they are all built up on each other, but there are several that are trying to explain how we see terrestrial gamma ray flashes. And it would be an advantage for us to study them from the ground, because it will give us an opportunity to look at them closer, in a way closer than we have been before by satellites about when we are 500 kilometers away. There has been only 6 crowned TGFs that have been studied up to today, and they are all happening after the return stroke, not more correlated with the leader. This gives us an idea that what we're seeing from the ground is different physics than what is seen by the satellite experiments, but that is before the telescope array observation. Telescope array observation by Okuda-san, he noticed that we have, what we should have is a normal SD trigger of 0.01 hertz. What we're seeing is 3 or more detection of events in less than a millisecond. Looking at this closer, we found out that this is related to thunderstorms, and a suite of lightning instruments have been implemented at the telescope array site, the LMA and the interferometer that we covered earlier, and a slow and fast antenna. The slow, they measure the change in the electric field per time, and if the slow antenna is the change in the electric field over the whole flash, and the fast antenna zooms in on more small times. And what you have right here is an observation by both LMA and the telescope array detector. This is the altitude of the sources versus time by LMA, the blue dots. The green line is where the telescope array has observed an event, several events right here. And this is where the return stroke. So as you notice, first, that the telescope array observation is happening at the first millisecond of the flash. This is more consistent with the leader stage of lightning. And this is the first observation by a ground experiment that is telling us that what we're seeing is consistent to the physics that the satellites experiments are seeing. It is happening a few kilometers above ground, and it happens with a similar duration to those of satellite experiments of a few hundred microseconds. So, another thing that we're seeing is that by the slow antenna is a consistency with what we're seeing by the lightning mapping array, which is that these events are consistent with the leader stage. So this is quite big, and the first time it got shown in a TGF meeting, everybody was completely surprised by this new result. We have, with the suggestion of one of our collaborators from New Mexico, is that what we're looking at seems to have very similar characteristics to something refers to as the initial breakdown pulse. Here is the fast antenna electric field measurements versus time, and they have a similar duration and separations to these high electric field pulses that are happening at the initial leader stage. This is why an interferometer was installed last year next to our detector. And what we saw, so if you focus on this green line, this is the fast antenna electric field measurements. And what we saw, an observation with the telescope array of a gamma ray flash. And it is, when you zoom in on it right here, you can see that it's very consistent to the initial break down pulses. This work is also going to be shown later on today, and it's in preparation for publication. So two things that the telescope array is contributing in the TGF world is that they are making the first observation to IBPs, making the first observation to the leader stage from ground experiments, and they have now the world largest sample of ground observed TGFs of about over 25 events. Another very interesting result that is coming out of GRAPES 3MT, in which the result also relates to powerful thunderstorms and TGFs. They use the mu1 component of the detector, and the mu1 component, they can reconstruct mu1s with 169 directions with an energy threshold of a GeV. They have a talk also in this afternoon today. In addition to their mu1 detector, there is also a suite of electrical field mills on the ground that is separated by a few kilometers apart that has been used to study these thunderstorms. And what they found out is that, so here, this is a display of their mu1 detector. This color scale is the relative intensity, blue is the deficit, and red is an excess. And what they found out is that when there are thunderstorms that are passing on top of their detector, that they have a deficit in the relative intensity of mu1s. And this deficit is because if you have a positive potential that is going on in your thunderstorm, then you have an energy loss in your mu plus and an energy gain in your mu minus. But because we have positive particles for cosmic rays, we are dominated by positive muons, and therefore the total is an energy loss inside the numbers. So what you have here is this relative intensity deficit is correlated with the fact that you have a thunderstorm passing by with a high potential on top of your detector. And this is a 2-minute snapshot, and it shows you how the thunderstorm is propagating on top of your detector. If you look at the one-dimensional projection of this relative intensity, this is versus time. This is the relative intensity. There is a red line right here that tells you the 1 sigma uncertainty. And what it shows you is that you have a deficit of about 20 sigma that is lasting over 18 minutes on top of your detector. This modeled by Monte Carlo, while varying the potential between -3 and +3 gigavolts with steps of 0.1, you can see that in order to arrive to a relative intensity deficit of -2%, you would need to have a 1 gigavolt potential that is in the thunderstorm brewing on top of your detector. This is a significant observation because nothing before it have ever seen a drop voltage of higher than 100 MV. So this is the first observation of its kind that is telling us that what we're observing, that the thunderstorms that we're observing is in the gigavolt potential. A very important fact is that Agile have observed 100 MeV gamma ray, and when it did that, one of the interpretations inside their paper is that we need hundreds of MVs of potential to explain this phenomena. And so this is consistent with what G3MT have seen. But another interesting fact is that they use the suite of instruments of the electric field mills, and they to understand the height and The size of this thunderstorm, so it was about an 11-kilometer height and about 400 kilometers square in size. This is about the same height that jets go and fly by in. They modeled the electric field as well, and there are many details inside this measurement that you can more see in the cosmic indirect talk later on today. This is just a video that just kind of summarizes the 2D plot with the 2-minute snapshots of how a thunderstorm passes by the G3MT detector. Okay, another very promising observation by OJ is that they are able to detect and document ELVs. ELVs are rapidly expanding optical rings that is thought to be from electromagnetic pulses produced by lightning. They are known to be in the bottom of the ionosphere between 80 and 90 kilometers. And they last for about a millisecond. And what the OJ detector discovered is that they can see ELVs through their fluorescence detectors. So this is an example of what a cosmic ray detection would look like, which we all know. And this is the detection of what an ELV detection would look like. They modified their trigger, and with this modification, they are able to see over 4,000 ELVs between 2013 and 2018. Now, right here, this is the ADC time, ADC versus time, and every single light right here is for a single PMT. And so some of them you can fit to a Gaussian, but they discovered with more observations of ELVs that you sometimes see double peaks inside these signals. So these double peaks right here is by this ELV, for example, from this PMT and this PMT. So if there is 10 of these observed inside one ELV, this is referred to as a multiple ELV. And the way they categorize it is that they measure this distance between these double peaks and the time of the first peak, and they plot them against each other. And what they see is that there are sometimes 4 categories to these observations. First is that the separation in time is small, is about 50 microsecond and constant. And this is probably referred to the electromagnetic pulse bouncing off of the ground. Another kind of classification is that you see the same thing, which is a constant time difference on top of your PMTs, but it's much larger. It's between 100 and 150 microsecond. And this would be referred to more to the possibly a very strong signal that is coming from lightning that could be from the initial breakdown pulse or the return stroke. Another observation that they're seeing is that some of these time differences are decreasing with time, and this is probably an overlap with another transient luminous event. One interesting class of events that they're seeing is that this time difference have a jump in it, and this type of class could be explained by a correlation with terrestrial gamma ray flashes, which is something that has been postulated in the field for a while. So in short, they are observing a rich variety of ELVs that are not completely understood, and the models are being developed continuously in order to try to understand them. The fluorescence detector recorded ELVs with a resolution of 50 times better than any previous observations. For more about this result, Professor Roberto Musa is showed a poster in this meeting about this result. Okay, so I want to leave you with the summary. Cosmic ray detectors have, this is a very exciting times of how they are now not only resolving the mysteries of the universe, but also resolving the mysteries in our own atmosphere. We have unprecedented measurements in mapping lightning, and we have breakthroughs in the origin of sources of TGFs that have been a question that's looming for decades now. We have the first evidence of a gigavolt potential. This is something that has been postulated by Wilson in 27, but G3MT is the first detector that had the first evidence of it. And we are observing thousands of ELFs with the OJ detector and modeling them and trying to probably zoom in onto their connections with other TLEs or TGFs. Thank you very much.
Thank you. We have time for some questions or comments. Yes.
Thanks for a very nice overview of all these phenomena. I think what we need also, just like the folks in other branches have done, we need a multi-messenger approach here, you know. Different groups have to talk to each other, which has not happened so far. Maybe then we can get to the bottom of the problem much more quickly.
Yes.
I have a separate question. I just happen to be sitting next to it. Well, it's a wonderful talk. Is there any postulated relation between the elves and the lightning? It's like they're almost a separate thing. Were they expected? Is there a connection to the lightning understood?
The elves and lightning, I think there are models trying to explain it, but and they're trying to explain it in relations to lightning, but the zoom in on the which part it is from or its relation to TGFs, there's still models brewing and observations is what's going to help us zoom in on it.
Had they been seen before? Are they
Elves have
actually
been
connected?
seen, yes, by photometry is when they were first observed, and also they're studied by satellite experiments as well. But OJ is contributing from the ground, which, as we saw, like in the telescope array example, it has advantages to see it from both places.
We have a question over here.
Thanks, Rasha, for advertising all these helps observation. I have a remark about the maximum energy seen by Agile, because I've been speaking with Martino Marisaldi, and Agile recognized that the maximum energy is actually 40 MeV. The 100 MeV, it was actually a pile-up of more gammas in the same event. So the maximum is completely consistent with the relativistic runaway breakdown theory of Dwyer.
Okay, so there was a follow-up paper to explain the 100 MeV?
Yeah.
Okay.
So the maximum is something like 40 MeV.
Okay.
And the explanation of the elves is pretty clear. I mean, as a phenomenon, is just related to the fact that the electromagnetic pulse emitted by the lightning, when it impinges the top of the base of the ionosphere, it accelerates electrons and these re-emit light. The interesting thing is that it's a possible signature of some of these elves that can be a signature for the emission of TGFs. That's an hypothesis that have to be proved. And I completely agree with the statement that we need a multi-messenger approach.
But my understanding is that this is not very easy to model. The signal that is observed is not very easy to model.
Yeah,
and this is why
the intensity is not so easy.
Yeah,
definitely.
And so
yeah,
this is those observations are important.
Yeah,
trying
definitely.
to zoom in on that, right?
But it's a very fast phenomenon, so It's just
Sorry?
a very fast phenomenon. Especially multiple elves are very hard to model, and that's
Yeah.
why it's.
Yeah.
Anyone else? No? Okay, let's thank Rasha again.